So okay, so welcome to our research seminar on software automatic tuning using machine learning. Today our presenter is Dr. Amir Ashuri. He's a postdoctoral researcher at ECE Department of University of Toronto under the supervision of Professor Tarek Abdurrahman. His research interests are deep learning, compiler optimization, automatic tuning. Prior to joining the U of T, he completed his master and PhD at Polytechnic de Milano under the supervision of Professor Cristina Salvano. His PhD thesis was selected as the winner of IEEE Italy section Best PhD Thesis of 2016. And recently, the book entitled Automatic Tuning of Compiler Using Machine Learning has been published from his PhD thesis.
Thanks a lot. Thanks for having me. Good afternoon, ladies and gentlemen. So today I'm going to talk about software automatic tuning using machine learning. So this is going to be the outline of my talk. So I'll start with the description of the problem, and the bulk of my presentation will be around compiler optimizations, and we're going to discuss two major problems involving it, optimizing compilers, which are optimization selection and the phase ordering problem. Then I'll have a few slides about my current research at the University of Toronto on accelerating deep learning applications. Right. Thanks, Andy. He already introduced me. So I finished my PhD in December of 2016, and my PhD was funded by a European project called Antarex. It was within the European Union's Horizon 2020, and as of January 2017, I was a postdoc. My funding comes from Qualcomm Canada and MITEX, and I'm working on accelerating deep learning applications for mobile devices. So my goal is to have optimized compilers so that they can execute codes faster and on a more computationally efficient way. All right, so let's start description of the problem. As you know, we rely on software, and software are running in various hardwares. So looking on the right side, on top right, so these can be high-performance softwares running on data centers, or on the left side, we might have softwares running on mobile devices. Also, there's a recent trend on wearable devices that are relying on domain-specific languages and domain-specific compilers in order to run mostly on fitness devices or other wearable devices that you see surrounding us. On the other hand, due to general scaling and also Moore's law, I'm not going to talk about the end of the scaling of Moore's law and also the dark silicon era. But in general, we see a trend, for instance, on the case of ST microelectronics, so that the hardware is getting squeezed every year. So starting from 2005 up to 2013, you see that they've been from 65 nanometers up to 14. And now we are having even smaller scale hardware. So we expect hardware also to have performance boost every 6 months or every 12 months. Within this puzzle, there is a missing component, which is compilers that are lagging to cope with the performance of softwares and the hardware as well. So there's a lesser known law called Proebsting law. So it was introduced by a professor at University of Arizona with the same name. And he was basically saying that compilers advances double every 18 years. So this is a huge gap between the compilers, which are the working module that connects both the hardware and software here. So he basically ran a small experiment. So he had a small code he used to compile with or without an optimization of the compiler, a cutting-edge compiler he used. And he divided the performance benefit of having optimization and without optimization with the same code, and normalized it by the number of years that we can expect that the compiler optimization domain was working on optimizing compilers, say for 40 years, 45 years. And he basically found that on average, we had a performance improvement of 3.6 per year, which comes because of that. So we have a huge misbalance. How are we going to alleviate this misbalance? And my bulk of the talk would address this lagging component. This will lead us to optimizing compilers and the problems involved with optimizing compilers. So, as you know, if you take a look at the compiler as a black box, so it's going to receive the source code and it's going to convert it in a way that the chip or the hardware understands the binary code that it emits. Right? If you zoom in into the module, you're going to have several layers within the compiler. You have front end, middle end, and back end. In the front end, it accepts different languages, high-level languages, depending on the compiler, so C, C++, Java, or other things. It's going to check the semantics and the context and the syntax, and the bulk of the optimization is done in the middle end. We have optimization in the back end as well, but it's outside the scope of my talk today. So in the middle end, they mostly target loop optimizations and also global optimizations. So let's see if we can use this type of optimization in this level and come up with a better code that we can generate using the same compiler, right? So as an example for a global optimization, I brought up a simple example of common subexpression elimination, or CSE. So suppose you have your code here. You have multiplication of B multiplies C, and it's being used twice here. So if you target this, you can simply avoid this multiplication every time. I mean, given some conditions. First of all, if the price of having a temporary variable must be smaller than the price you pay for the multiplication, which is the case for most of the time. And also the other case is B and C shouldn't be assigned after you computed the temp, right? I mean, we can gain this information by just running a control flow analysis. So now we can use temp as well every time we needed to use B multiply C. So this is a very simple case of a global optimization. So this, by global, I mean throughout the code. So this globally could be in a small block or in various blocks. So let's talk about a loop optimization. So I brought up loop unrolling here. So suppose you have to loop over the variable x and you want to remove it. So if you run it on the left side, you have to run it 100 times. But you can simply unroll the loop by a factor of 5 here on the right side. So instead of running 100 times, you can just divide the loop and run it 20 times. So it's going to improve the pipelining and reduces the penalty of the branches, given the condition that you don't have any dependencies within, that loop. Also, if you are targeting parallel computing or parallel domain, you can parallelize this as well. So you're going to gain huge performance out of this loop optimization. So let's talk about another problem within the compilation problem. So this is a piece of code I brought from Polybench dataset. It's a matrix multiplication. It's toward 2mm. And I generated the assembly file on the right side. Just for the sake of this talk, I try to map one-to-one the line 81 to 520, which is the hex number of the 81. I know that these are not mapping one-to-one, but just for the sake of the presentation. So they are matching the number. So compilation was known as translation, right? However, while we compile, we can optimize as well. We should optimize as well. So the right definition for that is going to be compilation is equivalent for translation plus optimization. While we translate, we can optimize. So suppose you apply your first optimization, just the CSE that I brought in a couple of slides before. So you're going to have this piece of binary emitted out of the compiler. If you use that loop optimization that I mentioned, loop unrolling, you're going to have another piece, right? What if you combine the first two? You apply CSE and then loop unrolling. Or the other way around. What if you had other optimization and you could combine them with repetition as well? So you see that simply by adding this optimization, you're going to have more and more combinations to the point that it's getting out of your control, right? So I'd like to tell you this simply by having less than 100 compiler optimization, we can generate many billions of different translation from a code that sounded very easy for us to generate at first, right? So let's go to the state-of-the-art compilation frameworks like LLVM, GCC, or Intel ICC. So in LLVM, for instance, we have around 160 optimization passes. In GCC, even we have more. So you see, the problem expands to a point that is manual construction of heuristics is virtually impossible. In the past, compiler designers used to brought up some manual manual sequences of optimization known as O-O levels, -1, O1, O2, O3, or OS. And throughout their trial and error, they found that these passes, on average, is going to be helpful if you use on several applications. But in most of the cases, the research has shown that we can simply easily outperform these standard flags. And we need to come up with a better, heuristics or machine learning-based models to construct based on the application we are, targeting. Because at the end, we are interested in optimizing certain metrics. Performance, by performance, I'm talking about execution time. In the past, code size was an issue in embedded domain. Now, not anymore. And in a way, we can optimize the power metrics as well. So this will lead us to have two major problems, which are known in the literature as selecting the right set of compiler optimization or the phase ordering of those passes. So let's start with the first problem, definition of the first problem. So it's called selection problem. We have several compiler passes. They form an optimization space. In this case, we disregard the ordering. We are only interested in identifying whether or not to apply this optimization. So suppose you have n number of optimization, and omega is your available optimization level for some of those n's. Like you have loop unrolling to the factor of 1, 2, and 3. So loop unrolling has 3 levels as optimization levels. So let's see a quick example of that. We have 5 optimization, and 2 of them has 3 optimization level. So our 5s are loop unrolling, tiling, CSE, loop fusion, and memory to register, right? So we can have one variation as all of the 5, no ordering. We disregard the ordering in this case. Another variant would be loop unrolling to the factor of 3, tiling 2, and loop fusion, and we disable the other 2. The other one would be just, sometimes we can only use loop unrolling once, right? And the rest are disabled. And you see, by having these 5 only, we have 72 different variants. And each of those variants can lead to another binary having a distinguished performance metrics. So now let's go to the harder problem, the phase ordering problem. As you see, the first time it was noticed in the literature, it was in late 70s, and it still is an open issue because in reality, there is no ideal ordering of phases because you can expand your optimization vector infinity. So there is no bound for your space, and there is no deterministic solution for that. Also, when you apply optimization B after A, it might obliterate some of the advantages that A could have been performed, right? So you have to make sure that the way you apply your optimization doesn't affect the prior one in your pass. So you see that the optimization space is way, way larger than what we had in a selection problem. Let's go to the previous problem. We have 5 optimization, and we limit our optimization vector up to 5 only. We're not interested in going forever. So our 5s are loop unrolling, tiling, CSE, loop fusion, and memory to register. In this case, also we enable repetition of an optimization as well. Sometimes there are some compiler optimization that you need to reapply another one after that. So this is CSE actually. Sometimes after, for instance, applying memory to register, you might need to have a dead code elimination after that as well. So the repetition of those makes sense. And you see by having these 5, and a length of 5 only, I have around 4,000 variants that I can play with my compiler, and each of them can lead to a different performance metrics. Some might run slower, some might run faster. They have different code size characteristics, and so on and so forth. So let's see what the research have been doing in the past, I'd say 30 years. So one of the well-known techniques that people have been doing as of late 90s, it was known as iterative compilation. So just like what the name triggers, we need to have several recompilation of the source code using different optimization flags and simply choose the best one we found, right? It's like having someone tossing a coin for you. By each toss of the coin, you're gonna generate a new optimization vector, and you're gonna apply it towards your code. And each of the codes has a distinct characteristics. Definitely, it has an advantage because eventually, if you go for a long run, like 6 months, you go for a year, normally it's gonna bring good results for you. And in its pure version, when you have just iterative compilation, you don't have any machine intelligence involved, and you can just run it depending on the application. Of course, it has a downside. It's very time-consuming. It has a high overload, and you don't have any transfer of knowledge here. So if you wanted to optimize your new application, you need to start from scratch. So all those months that you start to optimize the previous one, you have to trash them and start again. So can we do better? And that's exactly what my research is all about. So I'm employing machine learning based models to pair with an iterative compilation strategy to outperform iterative compilation itself, and I can transfer the knowledge towards other applications as well. So it's going to be application, data set, or hardware dependent. All right, so let's just have a quick definition for compiler autotuning. So autotuning stands for automatic tuning. So it states automatic code generation, code optimization, and also at the same time we enable various optimization scenarios. For instance, we are interested in minimizing the code size and maximizing performance. So historically in the 90s and 80s, it was done in the backend, but if you want to play with the backend optimization, you have to open up the compiler, and this is going to be a high overhead. And and it requires exclusive knowledge of the compiler designers, right? So state-of-the-art autotunings are now recently involved with using machine learning as a leverage. So I brought up here a sample autotuning framework. So this was from my latest survey that we just published in ACM Computer Saver. So in this survey, I surveyed over 250 papers of the past 25 years. So this is an example of an autotuning framework. You see on the left side, we start with training set. We define the way we are generating our versions using the design of experiment, or DOE. And then we pass it to the compiler. At the end, we have some binaries. We're going to capture the performance metrics, and we feed it in a model, the machine learning model. On the concurrent path, we need to extract the features out of those applications. I'll explain in a few slides what that is. And then an optional component within this process could be dimension reduction, PCA, factor analysis, or other techniques. And then we feed both cases to the machine learning model, and it's going to construct us a predictive modeling. So then we use the predictive modeling in our test examples, those on scene applications that we are interested to optimize. We redo the same feature extraction, and by just passing the features of the new application, it's going to bring us the predicted outcome. So the outcome could be the performance, the predicted speed up of that application without running it, or a sequence of optimization that we can apply to gain performance. So let me just quickly mention some of the more notable works in the state of the art. So as I mentioned, in the late 70s and 80s, there were some well-known papers that introduced the global optimization methods in the backend of the compilers. And in early 2000 and late 90s, Cooper started to use genetic algorithm on the compiler domain. And then when iterative compilation came to phase, they could pair these two. So we have several papers that are using machine learning models with iterative compilation. Then later on, Cavazos and E.J. Park started to use other type of features to use for constructing their machine learning models. And lately, there were some papers on phase ordering problem, and we could also contribute a little bit to the field by some work in phase ordering and also iterative compilation as well. So since I just don't want to run out of time, I'm going to describe two of my papers, one of them for selection problem, this one here, and also the other one for the phase ordering problem, so that you get to know better about my research. So first of all, let's start with the first one, the other work that tackles the selection problem. So we called it COBAYN, or the acronym stands for Compiler Autotuning Using Bayesian Networks. So the goal was to identify the best compiler optimization without disregarding the phases of the orders. So again, just like the sample figure that I mentioned, we characterize the applications. Each application passed through one set of characterization. We construct the model using the Bayesian network. So I'm not going to go into details, but please ask me if you needed further details. So we use Bayesian model to construct a probabilistic model out of the relation between the compiler, the application characterization, and the optimization vector as well. So we could marry these two words, and on the prediction on an unseen application, we need to pass the application characterization of that unseen application, and then we're going to sample from the Bayesian model, and that sampling will bring up us a new vector of optimization that we can apply for that unseen application. And this will bring a speed up for that application. So in a high level, in the training phase, we pass through characterization, dimension reduction, and model construction at the same time. We were only interested in filtering the top, in my case, top 15% applications in my data set, because I wanted my Bayesian model to be constructed with only good solutions. So when a new application comes, when an unseen application comes in a prediction phase, in a target application, given the evidence that I'm feeding to the model with its characterization, it's going to come up with a solution that was learned by top 15% of the rest of my data set. And it's going to come up with a prediction for the optimal solution that the model thinks I need to use to maximize its performance. So this is an example of finding patterns in my graph topology using a Bayesian model. So the first layer shown in pink up are the components of my application, so my PCs, principal components. So say these are the features of my application. I had 10. And using a Bayesian model, I could construct a model in such a way that I could relate my components of my application, which was unseen, to the optimizations and optimization itself together. So like you see, if you follow the blue path, you see that loop unrolling impacts on branch probability, and also on the left, on the red arrow, you can see that these two tree optimizations are interdependent as well, and these are actually making sense. So I could generate this for all the applications, and when I was sampling, this would lead us to a significant speed up over my data set, a data set of around 24 applications from Cbench, and I use also another benchmark called Polybench. So these results has been sorted by the performance improvement over optimization O3. So you have both O2 in blue and O3 in red. And you see that on average, I could outperform dash O2 by more than 50% and dash O3 by around 50%, given in my data set. Another comparison with the work of COBAYN and the set of the results. So this is actually the most cited paper of the field, and the other two were like the other two models here. So COBAYN could outperform those state-of-the-art papers by around a margin of 10%. So the results are in logarithmic scale, so you can see the expansion. So we both extracted 10 times, so we predicted 10 times from each of those distributions. So COBAYN, the Markov Oracle, IID, and random, and these are the comparison made at the point of 10.
So what's on the horizontal axis?
This is the number of predictions each of the model brought. So I fixed the comparison at 10 is as if you extract 10 times from COBAYN, you extract 10 times from that Markov Oracle, and you compare the best of the 10 of each of these models. It's like a top 10 accuracy, top 5, top 10. Because they reported top 10, I try to match those reporting so that I can have the comparison. All right, so this will wrap up my selection problem site. If you have any questions so far, I can follow.
What about the performance? You have been saying that what kind of performance numbers?
So in this example or in general?
In this example.
So this has been normalized because I explored all this space. So my overall space was around 128 points. So I knew what the maximum speed up was. That's why eventually all of them reached that maximum speed up. But the point is how we're going to reach that, how fast we're going to reach the maximum speed up. We are trying to reach higher speed up faster so that if you had an increased pace, you're always outperforming the rest of the models. That's why you see eventually these models are getting to the maximum, but the point is how fast we're going to reach theirs. So the one was the maximum speed up found, which is, in this case, these are the average, but you see here, my maximum speed up found was around 3x speed up. But on average, I was, outperforming around 50% the standard optimization.
So it's speed up in comparison to no optimization. Right?
Speed up. So all of the speed ups are in comparison with the standard optimization flag. Yeah, that's right. All right, so let's talk about tackling the phase ordering problem. So we talked about the phase ordering as the harder problem. It was it is still has been an open issue in the field for the past 4 decades. So by having 20 optimization, you see that we have more than 10 to the raise of 18 without even the repetition case. And so you see that it's a very significantly large problem. People have been trying to group their optimization flag in order to downsample their optimization space by random clustering or manual clustering first, and then they start their optimization process. So we came up with an automatic way of clustering first, and then we applied that to constructing our model. Before showcasing my other work, let me just describe what are the 2 techniques involved in performance prediction models, targeting the phase ordering problem. So we have one called intermediate speedup prediction. So it's going to predict the speedup at each intermediate step of the code. The other one is the full sequence prediction. So at one shot, it's going to tell you, you have this application, use this sequence, and it's going to bring you the performance that you were expecting from your model. So let's talk about the intermediate speedup model first. So suppose you have construct an intermediate speedup prediction model, and it won't stop unless it hits the stop condition. This could be reaching certain speedups like 1.3, 1.4, or you're interested in optimizing it 5 times, 10 times. That's the price you want to pay. So at first, your application comes. I showcase the program features in blue, and I deliberately put it in another color. So say it was not the baseline case, so it was already applied with other optimizations. So we started from an intermediate, state already. That's why this one was changed, right? So we are interested in finding the next optimization to apply on this program, given this set of features. So it's going to query my model, and my model tells me, because of this application features that you feed into my model, I'm going to predict at this point you can apply optimization A. This is what I'm seeing the most viable among the other optimization that I have in my space. So you apply A, and applying A, when you feed it to another characterization pass, you see that applying A change another component of my application now. So I have in the state of -A apply transform -A. I have to repeat the process again. I'm going to query my model. It's going to tell me at this point, given these program features that you're fitting, maybe you apply B here. So applying B again changes another components of my application, and I have to redo the process. The prediction model decides, okay, it needs in this case that we have another repetition of B, for instance. And the fourth time we hit the stop condition, and then through these processes we found that the final optimization given this application was A, B, and B. So that's one way to tackle optimizing a program iteratively using an intermediate speedup prediction. The other way, which we did in our latest work, 2017, was the full sequence speedup prediction. So when you have such a model, your features are all at the baseline, so you don't have to pass it in an intermediate step. And you're interested in, at one shot, interested to find those passes to use with that application. So your queried model at one shot is going to tell you, for this application with these features, directly use this for, and that's going to be your final optimization vector, A, B, B, and C. So let's see how does this approach works. All right. So in order to do that, as I mentioned, we started by clustering the available optimization inside O3. So O3, as I mentioned, is one of the standard optimization in LLVM. It has 150 optimization passes inside, for which 60 of them are unique passes. So it was tentatively, throughout the years, by compiler designers in LLVM community, they brought up, okay, you have to use this and that, and then they would just tweak with that. And after several years, we have this O3 that, on average, when you apply it on most of the applications, it's going to bring you speed up for you. So we thought, let's just start from a good enough, baseline. Instead of starting from 0 and you explore in the dark, you're going to start in an already optimized flags, let's say, and let's cluster those and reorder them using machine learning. Let's see if we can outperform O3 itself. So we passed through a process to construct an optimization dependency graph. So we check every pair of these 60 unique passes within that sequence, and we count them +1 every time this pass was consecutively appearing in that pass order. Like if you have loop unrolling here and CSE after each other, so this is gonna add up 1 to this matrix of counting. If you have another one later on, because you have repetition in O3, you're gonna add them up again, and then using that, you're gonna be able to generate an optimization dependency graph out of O3, and that was the result. So these are the 60 unique flags inside that, and the thicker the edge comes, you see that the more dependencies, the higher the number of dependencies among these two flags were inside O3. So now we know that tentatively compiler designers in the past 10, 20 years, they would come up with some solution. Okay, if you use maybe, let's pick up like prune this one as well here. normally it would always correlate it within line. And the thickness of the edge was showcasing this. So now we were able to apply a clustering method. It was an extension of k-mean. I'm going to go into details. If you needed further information, I can describe it. I have it in my backup slides. So we clustered this, and we came up with 5 mega subsequences. So we call them subsequence A, B, C, and E. So now, instead of targeting all those 60s at once, now we have to play around with 5 now. And these 5 are internally fixed, but externally, now I'm able to play with the phases, right? And I know that the starting point might not be the best, but eventually, if I play with the orders, I might come up with a better solution at the end if I pair this model with my machine learning model. So that was the exploration of those subsequences without applying any machine learning. So you see that, so I have 3 lines here as my baseline 01, 02, and 03 with my proposed subsequences. And this line is only my proposed MICOMP subsequences. As you see, it makes sense that I start in a way where it's, worst case performance because I don't have any baseline here. I have to start from scratch. But eventually you see that by playing with the orders, I'm able to outperform even 03 itself. So 03 stops here and saturates here at 1.1. But now I'm in a far better state at around 125. So around 15% I have an upper bound of performance I can play with, right? So now the question would be, how am I going to traverse my new optimization space and hop up through this line towards the region of interest? And this is where pairing a machine learning model help us in order to traverse this iterative, compilation theoretical, let's say, upper bound. So when I paired it with my model, again, the details on the paper, if you need further information, I can just provide you. So that was the final results when I paired it with my machine learning model. So my top 1 result could outperform the state-of-the-art paper, which was using ranking. And you see, if you go up to top 20, the trend shows that at each of those extractions, so 5 predictions, 10 predictions, 15 predictions, my comp was in a better state than the state-of-the-art paper. So you see that clustering help us to outperform the existing work, actually. So you might wonder, so what's the overhead involved with this process? As this is following a classic supervised learning method, so you have to have one offline training no matter what. So it's going to take some days because you have to generate your data, you have to generate your model, and you have to construct it. But once it was constructed and it's only been done once, then you can, in the online prediction phase, a new application comes, a new unseen application comes, and you can just apply it. And it's going to give you the performance that you expect. So on average, we calculated that this online prediction is going to cost you around 2 compilation and execution time. So this is the price you have to pay if you are using MICOMP in this case. It's as if, because anyways, you have to run it at least once to make it run. So the price you pay is 2 times the compilation and execution time. Finally, that was another set of results with the state-of-the-art work of John Cavazos and Samir Kulkarni. The data set we compared both cases was CBench. And you see on 26 applications out of 32, we were outperforming the other paper. And on average, this method, the full sequence speed-up prediction method, could bring on average 5% speed up on the execution time of the applications. All right.
But O3 has some reputation of passives, and you don't have, right? But you are clustering the unique set.
So O3, that's a good question. So O3 has 60 unique has 60 unique passes, but they have in repetitions. That's why in overall we have 157, right? So we use those 60 unique passes to generate an optimization dependency graph, and out of those we generated, using the clustering method, our subsequences, right? But now we can have the repetitions for our subsequences. Like we can apply 5 times 8, right? Yeah. But the point is, these are fixed internally, but we can play with the phases externally now, right? This way we could downsample the optimization space by a large margin.
But you created weighted graph, and weight you created based on the distance of 1
Right.
in the O3.
Right,
You
exactly.
go for higher distances in O3.
Right, yeah,
You
because
took the pair and then
that's right.
you
It's
measured the number of pairs and then
yeah, absolutely. It's like we reordered O3
Have
ourselves.
you ever thought about going like higher distance, like distance of 2 or 3?
Yes, actually. So yeah. So you see that when you apply the optimization passes and other things on top of them, you're already in a saturated state. You see, you're easily get saturated at the point of 1.5, 1.4, and no matter how far you go, like 4,000 more variants, you're still at that point, right? This way we could saturate in a way later time. Definitely we're gonna saturate, if you carry on, we're gonna saturate at 1.25. But the point is, now we have a better upper bound from here to here to play with the upper bound we can get theoretically. And we can pair this with a machine learning model. So there was other, I was thinking about not using actually O3 at all and see if you can just start from the random ordering of all the available optimization. But definitely with a random optimization, you should go carry on maybe for 1 million times so that you gain around 1 speed up. So like going back to the baseline, right? So it would take us longer. That's why this way we could start from a good enough point, but reorder that and come up with a customized reordering based on the application we have. All right, so this will wrap up my compiler optimization section. I'll have some very few slides about my current research that I'm doing in my postdoc on accelerating deep learning applications. So we're going to shift a little bit towards deep learning models now. So as you see, the growth in number of parameters, the number of convolutions, and number of operations we need to compute the state-of-the-art CNNs or convolutional neural networks, as starting from the LeNet 5, which was introduced in '98, up to, for instance, ResNet 50, which was proposed 2015. Now we have NASNet as well, like more latest generations of networks. So you see that the number of parameters and number of convolutions have started to expand significantly, right? Also, number of max or multiply and accumulate operation has been expanded significantly as well. So starting from in the order of Ks, now we are in the order of gigs, right? So definitely there is a need to find a way to compress and prune machine learning models, because eventually most of the instances of usage of these models are going to be on mobile devices. Your smile detection, your face detection, other things that you do every day on your cell phone. So the industry has gone towards the path that they're trying to use the hardwares on the mobile devices in order to do the prediction, rather than do the prediction on the cloud systems and you download the prediction from them. So in order to be able to deploy those models on mobile devices, which you have limited capacity, both on memory and data, so you need to prune the models, right? So my bulk of the work in my postdoc and also with Qualcomm Canada is we are interested in finding ways we can deploy these models on mobile platforms. So by doing that, we need to prune the model So we need to find a way to get rid of some of the parameters and find a trade-off between the prune model with the compressed size and also some accuracy that we lose with this process. So yeah, and it's going to be a trade-off. So let's see how does that work. So this is a histogram of the weights in the last computational layer of Inception version 3. You see the bulk of the parameters are centered around 0. And so like they're so close to 0 at some point you can just ignore them. So like 5.50 and in order of 10 to the minus 5 or minus 4. So without one of the famous techniques that you can apply here is for pruning is called the sparsification. You apply sparsity, you introduce sparsity towards your model. So, and for instance, depending on the window you want to sparsify, depending on the type and the strategy you have, you can find a range and sparsify this range. So you put all the parameters within that window to 0. So later on, you'll be able to find, when you are computing your multiply and accumulate operations, you can see, okay, I hit 0, so instead of applying a 0 and multiply it and accumulate a 0, I'm just going to ignore that operation as well. So I'm going to realize what I fed into the model as 0, and I'm going to realize and ignore those computations involved with that. And this is going to save a huge amount of operations and computation as well. So the way we implemented that window that I mentioned by several different threshold methods, depending on the geometric shape. So we call them flat threshold, triangular threshold, and relative threshold. And we prune those models on the fly. So you input the dense model. Our methodology brings us to a sparse model. So depending on the sparsity strategy, we sparsify that model given these ranges. And this is going to be the sparse pre-trained CNN. And then we're going to evaluate that to see how much compression we got and what's going to be the upper bound of the benefits we can eventually get if we realize that on the device. So this is some of the results for our pruning framework. So on the top left side is AlexNet, you have Inception v3, you have VGG, and you have ResNet. So by only affording to lose 5% from your top 5 accuracy, so that blue line represents the margin that we are affording to lose. So say you have a smile detection on your mobile devices. And if you lose 1 smile or 2, it's not going to be that catastrophic, right? It's not a driverless car that you're going to hit somebody. So in many of the domains, you can afford to lose like 5%, 10%. But by using that 5%, you're going to compress it as an upper bound by 3x, right? And the computation is going to be decreased as well. So it's very important for industrial, marketing as well, that you can save more battery, you can run it faster. So it's going to bring you, more attention towards your deep learning application that you're running. And this is exactly what we are doing. So we are on the final phases of realizing this upper bound, so that we avoid the computations that are involved with computing 0 and accumulating 0. All right, so I'm mostly done. I'm just going to wrap up my presentation with some speculation and future works. So on the compiler optimization domain case, it would be, so now we have heterogeneous word. We are using more GPUs. We are using DSPs in mobile devices. We are using FPGAs. So we need to expand our auto-tuning strategies from CPU only towards heterogeneous auto-tuning as well. We need faster and more accurate models. So we need to use the supercomputing powers, more recent and cutting-edge deep learning models like LSTM. We had a couple of papers recently using those. So this is going to be the future work and the path the industry and research community is trying to go to use more cutting-edge models to characterize and construct better and accurate models. On the case of the deep learning application domain, there are, as I mentioned, deep learning models are getting more complex. and you saw the trend starting from blended 5 up to ResNet, NASNet. We have more complex models. We need to deploy them. We need to be able to deploy them on mobile devices. So other pruning techniques like sparsification, discretization, quantization, and momization are going to be handy for us. And this is the path I'd like to carry on my research as well, to come up with more energy and computationally efficient model to be deployed on mobile devices as well. And if you marry the two words, you're going to find a holy grail. So you're going to have efficient compilers that supports automatic tuning out of the box. It's going to be very nice if you will have it in the future. Certainly, we are going towards that. And also, compilers that are able to generate high-performance code for deep learning applications and for mobile, for multiple target domains. Right. Thanks a lot for your time.
Thank you.